My name is Saori Yagyu, and I'm the account executive for the public sector in Japan at Amazon Web Services. My role is an advisor to higher education and research institute customers on cloud strategies. It's great to have you join us today for this particular session, Accelerating the Pace of Research for Kyoto University. Our first reference on AWS in Japan, analyzing human genome. Now, there's a lot to cover today, so let's get started. First, let's take a look at several use cases of an academic research institution in Japan. AWS Cloud is used for a variety of purposes. As a backup system infrastructure, such as ERP, as a learning management system and e-learning infrastructure, for research projects that require high-performance computing, telework infrastructure, and as a backup. The provision of the Signet Cloud Connection Service has had a major impact on the adoption of AWS Cloud among Japanese academic and research institutions. Signet, Japan's national research and education network, is directly connected to AWS. Therefore, customers can use cloud safely. By connecting to AWS in a closed network, AWS can be regarded as a part of university's facilities, which called the virtual campus. The closed network is important for the virtual campus when handling the sensitive data, such as human genome. AWS provides an extensive service portfolio to support researchers who need high-performance compute. With AWS Parallel Cluster, organizations can build high-performance compute environment quickly on AWS. Furthermore, with AWS Batch, organizations can fully manage batch processing at any scale. And lastly, with Amazon FSx for Raster, organizations can enable a fast and scalable shared storage to power compute workload. All these services are used by Kyoto University and developed by AWS Professional Services. Our AWS Professional consultants can provision and enable the right services for your business requirements. By collaborating with AWS Professional Services, Kyoto University was able to quickly deploy and meet the scale and compute required for its research. Today, speaking together with me is Professor Masao Nagasaki. He is a professor at the Center for Genomic Medicine, Graduate School of Medicine at Kyoto University. Kyoto University is the second oldest national university in Japan and has produced a lot of researchers to date. Today, as a use case of life science research using cloud strategies, he will talk about the realization of a genome analysis platform on AWS in a hybrid environment.
Thank you, Saori. The title is Accelerating the Pace of Research in Kyoto University. My name is Masao Nagasaki from Center for Genomic Medicine, Graduate School of Medicine, Kyoto University. The Kyoto University is one of national universities in Japan and launched 100 years before with several Nobel Prize researchers. For example, Tasuku Honjo as PD1 and Shinya Yamanaka as IPS. The agenda is as follows. First, Center for Genomic Medicine, in short, CGM, research project in Kyoto University. Second, the construction of hybrid cloud system with supercomputer system and AWS cloud. Our Center for Genomic Medicine, is conducting research to discover new knowledge by analyzing large-scale heterogeneous data in the life science field, especially human genome, omics, and medical records. The data size is tremendously increasing and large-scale computational resources are required. To solve the research questions, we are using the knowledge of information science, mathematical statistics, and genomic medicine. The target is common diseases, rare diseases, and cancer. The main core projects in our center are prospective genomic cohort study with 10,000 scale, and construction of national platform for rare disease data registry of Japan, in short, RADARJ. The first core project is a cohort study named Nagahama Cohort Study. The location of Nagahama City is shown in the map in the left. The location is near from our Kyoto City, the place of Kyoto University. The chair of this project is the head of a center, Professor Matsuda. The population size in this cohort study is 10,000, and the study was launched more than 10 years before in 2007. To the participants, we are collecting blood samples, questions and answers, and clinical information. The follow-up is every 5 years, and now in the second follow-up. Also doing whole genome sequencing, transcriptome, and metabolome data measured from the whole blood or plasma. Especially for this data is very large, and since need the implementation of hybrid cloud system, including AWS. And this is my main talk. The second project is to construct the national platform for rare disease data registry of Japan, RADARJ. In Japan, there are approximately 300 projects conducting research on rare disease supported by the Ministry of Health, Labor and Welfare of Japan, and the Japan Agency for Medical Research and Development, in short AMED. Diverse data, including clinical, genomic, and sample-related data, are generated by this project. However, at present, such data are managed individually by each project. This makes it difficult for third parties to ascertain the data generated by project. The mission of RADARJ is to integrate this clinical, genomic, and sample-related data generated by this project in one platform with a generalized informed consent from participants. Also, future promotion of joint research and the secondary use of shared data to accelerate research into diagnosis and treatment technologies for the improvement of quality of life to participants with rare diseases. For the detail, please refer to the technical report of RADARJ. Especially the advancement of human genome sequencing technology, we can obtain the whole genome sequencing information within a day. Also, using one latest sequencing machine, thousands of samples can be obtained in 1 year. Our two core research projects, the information of human genome from each individual, is very important. Currently, for the first core Nagahama cohort studies, thousands of samples were sequenced. For the second core project, also thousands of samples were sequenced. In very near future, tens of thousands will be sequenced. The trend is the same in worldwide, and in US and UK already sequencing around million whole genome samples. The size of human genome sequence data is increasing. The slide shows the increase of the rate of human genome from 2013 to 18 in the public database in US. In 2013, the size was 1 petabyte. In 2016, the size was reached to 5 petabyte. In the 2012, the size reached to 12 petabyte. Recently, parts of these public datasets are maintained on cloud. The plot shows the total studies from 2007 to 2017. As in this figure, the total numbers of genome research are increasing year by year. Also, the sample size to each study is also increasing. The blue bar means more than 0.1 million samples in one study. As in the former slide, the size of human sequencing data is drastically increasing. If you would like to know more detail in genomic medicine field, please refer to my recent publication. From now on, my talk focuses on the implementation of hybrid cloud system in our center to handle these datasets. Let's go to the next topic, hybrid cloud system with supercomputer system and the AWS cloud. And why AWS? To design the hybrid cloud system on our center, our PI members discussed the requirements and set 6 points. First is the scalability for large-scale genomic and omics datasets. Second is to maximize advantages of cloud and on-premise and also supercomputer system. Third is once right, runs all environment. Our responsibility is both education and research. From these reasons, other data sharing to joint degree students and researchers, including abroad, are important. So we have set 6 points. Then why use AWS? At first, to construct the hybrid cloud system, the network stability, security, and speed are important factors. In Japan, there is a high-speed low-latency network for academic named SciNet 5. When we have designed the system, the AWS regions in Japan already connect to the SciNet 5. Also, several institutes had experience to connect the SciNet 5 from their institutes with Direct Connect framework. The factor is very important to select AWS. Secondly, AWS has a long history of cloud, and since many documents exist in worldwide. In addition, many functionalities are implemented from the request by users, not only limited from academia. For other reasons, please read my slide. Well, then go to the next topic, the design of hybrid cloud architecture in our center. Our center mainly uses 3 locations. First, security VPC region in AWS. Second, the on-premise servers in our center, and supercomputer system in Kyoto University. Third, the supercomputer system in the University of Tokyo. For the specification of each region, please read my slide. All these 3 regions are connected by using SciNet 5, as I mentioned in the previous slide. Okay. The VPC region in AWS connected by using Direct Connect out the VPN. These three regions are divided into two units with their roles. The function of Unit 1 is run workflows for robust data processes and analysis to human genome and omics data. In contrast, the function of Unit 2 is run standardized data processes and analysis to human genome and omics data. As Unit 1, AWS, our on-premise in Kyoto University, and virtualized environment in the University of Tokyo are using. As Unit 2, supercomputer system in Kyoto University and the University of Tokyo are using. The benefit of Unit 2 is high-performance data processing and analysis. The benefit of Unit 1 is flexibility, once write, run anywhere, and on-demand resource assignment, especially on AWS. Sometimes, in Unit 1, resources are occupied by other users and take long waiting time to process the job. For the implementation, two key technologies are using. One is a de facto standard workload manager, SLAM. The other is a container engine, Singularity, which enables reusability, reproducibility, and reliability. For the part of details, please refer to our paper. As in this figure, in our hybrid cloud system, these two key technologies are implemented. On Unit 1, all three regions install SLAM and Singularity. On Unit 2, Singularity is requested from me and now runs on both platforms. Okay, the draft overview of design and implementation were informed. Then go to the next topic, the data flow of sequenced genome data analysis on the hybrid cloud system. For the analysis of sequenced genome data, both units 1 and 2 are related. First, sequenced data sets from our center or outsourced company are copied to our on-premise server and pre-processed. Second, the data is temporarily transferred to supercomputer system on University of Tokyo and applies the standardized analysis. Third, the data is transferred to on-premise and supercomputer system on Kyoto University and applies the downstream analysis. Fourth, the analyzed result is transferred to the secure VPC region in AWS to enable the in-house database search. Now implementing the functionality using the Elasticsearch database. This is the data flow of omics data analysis. Mainly, omics data is analyzed on Unit 1, especially on AWS system. Rare disease diagnosis service from patient image data is constructing. For the omics data analysis, workspaces of Windows OS is now in trial period. Workspaces systems are useful since the memory and CPU resources can be changed on demand. The slide summarizes mainly using functions on AWS. As database, I don't mention but using RDS as RadarJ and MacLogic for in-house data management. For AI-related matter, using EC2 GPU nodes. For SLAM on AWS, implementation of parallel cluster in AWS is customizing. This is a summary of my talk. First, the innovation of human genome sequencer increases the scale of production of genomic data. In first core study cohort project, thousands are sequenced. As the second core studies, as rare diseases, thousands are sequencing. Second, need to process and analyze these data sets in our center. Third, our solution is hybrid cloud system with AWS. The key technologies are used to manage multiple units with one unified operation. As part of hybrid cloud system, AWS is taking one important responsibility. Every year, all technologies in on-premise, supercomputer system, and AWS will progress. With the progress, our center will also actively optimize the role of these regions based on 6 requirements, as I mentioned. Thank you. For the development, many technical staffs and researchers are related. I would like to thank all these members. Also, I would like to thank for the technical support from these companies. If you have any questions, please contact. Thank you.
Because we've been this way from the start. Because the solution for one can be harnessed by others. Because clouds that compete can still connect.